Welcome back, children. See, in today's class, we'll be studying about radioactivity. See, while studying about average binding energy curve in the previous class, we have discussed that elements which have very high mass number show a phenomenon of radioactivity, okay, wherein they start emitting alpha, beta and gamma rays spontaneously and attain stability. So, in today's class, we'll be studying in detail about radioactivity, properties of alpha, beta and gamma rays, what is radioactive displacement law, and then later on we'll study about alpha decay, beta decay and gamma decay in detail. So let us start with what is radioactivity. Okay, look at the definition. Radioactivity is defined as it's a spontaneous emission of alpha, beta and gamma rays by a radioactive substance. So it is a spontaneous phenomenon, not a stimulated process. The element by itself starts emitting this alpha, beta and gamma rays. Because this was the phenomenon which was accidentally observed by Becquerel, we also call these rays as Becquerel rays, named after the scientist. Coming to the properties of alpha, beta and gamma rays, look at the below table. Property is mentioned on the left side, then for alpha, beta and gamma rays. So to first begin with the nature, alpha particles are a group of 2 protons and 2 neutrons put together with opposite spin. It is actually the nucleus of helium. Then beta particles are electrons coming from the nucleus. I again repeat, these are the electrons from the nuclear source, not from outside the nucleus. They have energies much higher than the electron energy. Then gamma rays are electromagnetic radiations. Coming to the charge, alpha particles are dye-positive, whereas beta particles are negatively charged, 1 unit negative charge. Gamma has no charge. Mass is 4 atomic mass units for alpha particle, and it is mass of electron for beta. In AMU, it is 0.00055 atomic mass units, and the rest mass of gamma particle is 0. Coming to the speed, gamma rays travel with a very high speed, 3 into 10 power 8 meter per second. Whereas beta will have lesser than that, 10 power 8, and alpha will be much lesser than that, that's 10 power 7 meter per second. Penetration power, alpha has less penetration power because it is heavy, and gamma has the highest. Ionization power is reverse. Alpha particles have high ionization power, whereas gamma do not ionize the substance. Beta has a medium or moderate ionization power. So one more point you can add. Alpha and beta particles are particle radiations. They get deflected by electric and magnetic fields since they are charged, whereas gamma are undeflected by electric and magnetic fields. So these are some of the properties of alpha, beta and gamma rays. Now let's look into the Soddy-Fagans law, or also called as radioactive displacement law. Okay, these 3 statements put together, we call them as radioactive displacement law. Look at the first statement. When a radioactive nuclide emits an alpha particle, its atomic number decreases by 2 units and mass number by 4 units. I told you alpha is represented as 2He4. If it is removed from the nucleus, atomic number is decreased by 2 units and mass number by 4 units. Therefore, the element is displaced 2 places left in the periodic table. Whereas by emitting a beta minus particle, atomic number increases by 1 unit with no change in mass number. So the element is displaced 1 place right in the periodic table. And by emitting a gamma particle, there will not be any change in mass number or atomic number, but there will be a change in its energy. Okay, so these 3 statements, we just call them as Soddy-Fagans laws or radioactive displacement law. Now let us come into details of each of the decay. What exactly happens during alpha decay, beta decay and gamma decay? As I already told you, alpha particles are a combination of 2 protons and 2 neutrons with opposite spin. So inside the nucleus, a group of 2 protons and 2 neutrons form a single unit, and then they come out of the nucleus. So during an alpha decay, see what happens to the atomic and the mass number of the nuclide. See, observe this relation. ZXA is the parent nuclide, Z is the atomic number, A is the mass number. if it is releasing an alpha particle, okay, this is the alpha particle, what is happening to the mass number and atomic number of the daughter nuclide? Okay, daughter is Y, Z minus 1, Y, A minus 4, along with a release of energy which is represented as Q value. Okay, here Q value represents energy released in the process. Okay, to understand this alpha emission, it is classically, by using classical mechanics, we cannot explain the emission of alpha particle from the nucleus, because to come out of the nucleus, the alpha particle has to cross a potential barrier whose height is 25 mega electron volts. Okay, so this diagram shows the height of the potential barrier. Okay, it's just indicated like a square or a graph whose height is 25 mega electron volts. But the existing energy with the alpha particle is much lesser, around 6 to 8 mega electron volts. So having 6 to 8 MeV, if it has to cross a barrier of 25 mega electron volts, it's very difficult and it is impossible to explain it by using classical mechanics. But it is being explained by a phenomenon called tunneling effect, which is a quantum mechanical solution. According to the tunneling effect, suppose you have a hill and a person has to cross from one side to the other edge of a hill. It is only possible if he climbs the hill and then comes on the other side. The other possibility is tunneling effect. Okay, the meaning of tunneling effect is, you can just understand it logically like this. If a person is on this side of the hill, he can dig a tunnel in it and then come out on the other side without crossing the potential barrier. A similar phenomenon is explained by quantum mechanics. So you can observe this graph. In this graph, if this is your width of the potential barrier, okay, so this distance, I'll call it as width of the potential barrier. On either sides of the potential barrier, the solution of or potential energy is varying sinusoidally. Even this side it is sinusoidal. But inside the potential barrier, how is potential energy varying? It is exponentially decreasing. I again repeat, it is sinusoidal outside on either sides, but inside it is exponential decay. Because of this solution, it is possible for the alpha particle to come out of the tunnel without crossing the height of 25 mega electron volts. So this is called the tunneling effect. Now come back to the Q value, what I told you before. You can evaluate the Q value by using mass defect or mass energy equivalence. So Q value is equal to mass of reactant minus mass of products into C square, or you can also write mass of reactants minus mass of products into 931.5 in mega electron volts if masses are measured in atomic mass units. So this is a formula to evaluate the Q value or the energy released in the process. And using conservation of momentum and kinetic energy, you can also find the kinetic energy of alpha particle by using this relation. You can remember it, kinetic energy of alpha particles is A minus 4 by A into Q value. First evaluate the Q value, then based on Q value you can find kinetic energy of alpha particles. And if you want to evaluate these relations, suppose you want to find out how this equation is being derived, you can use these two relations, conservation of momentum and kinetic energy. So it's my into Vy. Okay, just before emitting an alpha particle, if the parent is stationary, after emitting an alpha particle, momentum of helium particle, that means momentum of alpha particle, should be equal to momentum of the daughter nuclei from conservation of momentum. Then from conservation of energy, it's kinetic energy of alpha particle plus kinetic energy of Y. I think it should be Y. Okay, half my Vy whole square should be equal to Q. Okay, so solve these two relations, you can find the kinetic energy. So these are the things that you need to remember for alpha decay. Putting the points together, alpha particle is a combination of 2 protons and 2 neutrons. Atomic number decreases by 2 units and mass number by 4 units. Classical mechanics could not explain the emission of alpha, but quantum mechanics explains it by tunneling effect. And during the process, energy released is called a Q value, which can be evaluated by mass defect or mass energy equivalence. And then you can find out the kinetic energy from conservation of momentum and kinetic energy for the alpha particles. So this is all about alpha decay. Now let's come to beta decay. In beta decay, we define it as spontaneous emission of electrons or positrons by a radioactive nuclide. There are two types of beta decay. One is beta minus, we write it as beta minus, and the other one is beta plus. First look at beta minus decay. Elements whose n by p ratio is greater than 1. That means neutron number is more and when compared with proton number. Okay, one more method of explaining stability is by using n by p ratio. Nuclides whose number of neutrons by number of proton ratio is equal to 1 or close to 1 are found to be highly stable. So if n by p ratio is greater than 1 or less than 1, they are unstable and they try to attain stability by achieving this number as equal to 1. So elements whose n by p ratio is greater than 1 have a high tendency of showing beta minus decay. So beta minus decay is emission of electrons by the nucleus. Now let's see how electrons are coming out of the nucleus. We know electrons are not present inside the nucleus. So just before emitting a beta particle, what exactly happens inside the nucleus is a neutron splits into proton and electron. Proton will remain in the nucleus, this electron will come out. So as a result, tell me what's happening to the neutron number. Number of neutrons, one neutron is decreasing and one proton number is increasing. So that n by p ratio may approach the value of 1. But along with electron, we always add a particle. This is called antineutrino. Antineutrino is to compensate the energy. All the beta particles which are coming from the nucleus do not have same energy like alpha particles. They have different energies. To compensate this energy, Pauli has explained that along with this beta particle, some other particle, energized particle called antineutrino is accompanied by emission of electrons. So this is to compensate energy. So look at the reaction now. By emitting an electron, ZXA is the parent nuclide. It is emitting minus 1E0, it's an electron. Atomic number is increasing by 1 unit. And there is no change in mass number. But along with this, always try to add this antineutrino, because you can observe in the below graph how kinetic energy and number of beta particles are varying with each other. See, on y-axis we have taken the relative number of beta particles, and on x-axis their kinetic energies. So you observe the nature of graph is a curve which is not having any uniformity or constant value. So the gap is filled by adding a antineutrino. This is all about beta minus decay. Now look at beta plus decay. Beta plus decay, it's emission of positrons. So first look at what are positrons. Positrons are positive electrons. They have the same mass as electron but charge is positive. It is considered to be an antiparticle of electron. So the nuclides whose n by p ratio is less than 1 have a tendency to show beta plus a decay. Greater than 1 will show beta minus, whereas less than 1 are showing beta plus a decay. Look at what happens before emitting a positron. A proton is splitting into neutron and positron along with neutrino. For electron, it is antineutrino. For proton, positron, it is neutrino. Okay, these two are also antiparticles of each other. The same logic, all the positrons emitted do not have same kinetic energy. So to compensate that energy gap, we are adding this neutrino. So look at what happens to atomic number and mass number. By emitting a beta plus particle, that's 1E0, atomic number increases by 1 unit. Okay, it's not decreasing, it is increasing by 1 unit. ZXA gives rise to 1E0 plus Z minus 1YA plus neutrino. So this is your beta plus decay. There is one more possibility for elements with n by p ratio less than 1. If beta plus emission is not energetically permitted, then to attain stability, the nucleus of this radioactive nuclide will capture the nearest electron. So which electron is nearest to it? The first orbit electron, that is K shell electron, is very close to the nucleus. The nucleus will capture this electron and this electron will be neutralizing a proton and increasing the neutron number. Again I repeat, if n by p ratio is less than 1 and beta plus emission is not energetically permitted, what does this element do? It will capture the electron from the first orbit, that is the K shell. Since it is absorbing or capturing the electron from the K shell, we call this process as electron capture. So look at this, ZXA is the radioactive nuclide. It is capturing an electron. Atomic number is still decreasing by 1 unit and mass number has no change. So this process we call it as electron capture. And whenever there is a vacancy in K shell, the electrons in the next orbits like L shell, M shell and N shell will try to jump and fill up the vacancy, and they release the energy in the form of electromagnetic radiations. And that electromagnetic radiations we call it as X-rays. Okay, X-rays, it is always followed by emission of X-rays. Now coming to gamma decay. Generally gamma decay is always preceded by alpha or beta. That means after alpha and beta decay only gamma decay takes place. So during an alpha or a beta decay, the daughter nucleus whatever is formed, okay, whatever we are writing y, z minus y or z minus 2, the daughter nuclide is having excess energy and it is supposed to be in its excited state. Okay, that's possessing more amount of energy. That excess energy is released in the form of gamma rays. We know gamma rays are non-particle radiations, they are electromagnetic radiations. So when a nucleus comes from an excited state to the ground state, it is releasing energy in the form of gamma rays. So there won't be any change in atomic number or in the mass number. We can look at this example which is given in your NCERT. A cobalt 2760 is emitting a beta minus particle and it converts into nickel. And this nickel obtained will be in an excited state. Okay, so here we get nickel which is in its high energy state. Because it is possessing little higher energy, it will come down to the ground state by emitting two energies. Okay, we have shown two energy levels, E1 and E2. E1 is 1.17. So this is a gamma particle with energy 1.17 mega electron volt. If it jumps from this energy to this energy, then it will release 1.33 mega electron volts. If the nuclide directly jumps from this orbit to ground state, then the total energy release will be 1.17 plus 1.33 mega electron volts. So these energies only we call it as gamma rays. So in gamma emission, as we have discussed, there is no change in atomic number and mass number. So gamma ray is always preceded by a beta or an alpha decay. So this is all regarding alpha decay, beta decay and gamma decay of a radioactive substance. So this is all in radioactivity. So in our next class, we will study about radioactive disintegration law. Okay, there are two laws for radioactivity. One is displacement law, other is disintegration law. We have done the displacement and alpha, beta and gamma decays. We'll go into disintegration law in our next class.